Another day, another story. Summary. A new study reveals how our brains recognize and predict musical sequences, activating areas related to sound, memory, and emotions. This understanding could help develop tools to detect cognitive decline and dementia. The study measured brainwaves of 83 participants, showing the complex neural processes involved in music perception. Future research will explore how these mechanisms change with age and cognitive impairments. Welcome to Tabo Eminent Channel. Key facts. Complex brain activation. Music recognition involves sound, memory, and emotional processing. Potential for dementia detection. Findings could help develop screening tools for cognitive decline. Study details. Brainwaves of 83 participants were measured while they listened to music. Ever heard just a snippet of a song and instantly known what comes next? Or picked up the rhythm of a chorus after just a few notes? New research from the Center for Music in the Brain at Aarhus University and the Center for Eudaimonia and Human Flourishing at the University of Oxford has uncovered what happens in our brain when we recognize and predict musical sequences. When we turn on the radio and our favorite song starts playing, our brain reacts in a complex pattern, where areas that process sound, emotions, and memory are activated. In a feed-forward and feedback loop, our auditory cortex first responds to the sounds and sends information to other brain areas, like the hippocampus, which is involved in memory, and the cingulate gyrus, which helps with attention and emotional processing. This process helps us recognize songs quickly and predict what comes next, making listening to music an enjoyable and familiar experience. Knowing how our brain reacts to music can play a pivotal role in understanding our cognitive functions, explains one of the leading researchers behind the study, Associate Professor Leonardo Bonetti from the Center for Music in the Brain at Aarhus University. Our research provides detailed insights into the brain's ability to process and predict music and contributes to our broader understanding of cognitive functions. This could make a difference for studying brain health, as it offers potential pathways to explore how aging and diseases like dementia affect cognitive processing over time. In fact, understanding how our brain rocks along to Bohemian Rhapsody or reacts to a childhood classic may help researchers detect dementia in the future. In the long run, these findings could inform the development of screening tools for detecting the individual risk of developing dementia just using the brain activity of people while they listen to and recognize music. In the study, the researchers measured the brainwaves of 83 people as they listened to music, and they will follow up with additional studies, says Leonardo Bonetti. Future studies could explore how these brain mechanisms change with age or in individuals with cognitive impairments. Understanding these processes in more detail could lead to new interventions for improving cognitive function and quality of life for people with neurological conditions. Spatiotemporal Brain Hierarchies of Auditory Memory Recognition and Predictive Coding, by Leonardo Bonetti et al. Nature Communications. Abstract. Spatiotemporal brain hierarchies of auditory memory recognition and predictive coding. Our brain is constantly extracting, predicting, and recognizing key spatiotemporal features of the physical world in order to survive. While neural processing of visuospatial patterns has been extensively studied, the hierarchical brain mechanisms underlying conscious recognition of auditory sequences and the associated prediction errors remain elusive. Using magnetoencephalography, MEG, we describe the brain functioning of 83 participants during recognition of previously memorized musical sequences and systematic variations. The results show feed-forward connections originating from auditory cortices, and extending to the hippocampus, anterior cingulate gyrus, and medial cingulate gyrus. Simultaneously, we observe backward connections operating in the opposite direction. Throughout the sequences, the hippocampus and cingulate gyrus maintain the same hierarchical level, except for the final tone, where the cingulate gyrus assumes the top position within the hierarchy. The evoked responses of memorized sequences and variations engage the same hierarchical brain network, but systematically differ in terms of temporal dynamics, strength, and polarity. Furthermore, induced response analysis shows that alpha and beta power is stronger for the variations, while gamma power is enhanced for the memorized sequences. This study expands on the predictive coding theory by providing quantitative evidence of hierarchical brain mechanisms during conscious memory and predictive processing of auditory sequences. Our brains recognize and predict musical sequences through a complex interplay of various cognitive processes involving memory, pattern recognition, and predictive coding. Here's a detailed look at how this happens. Memory and familiarity. Short-term memory. As we listen to music, our short-term memory helps us retain small snippets of music, allowing us to recognize patterns and predict what comes next. Long-term memory. Over time, our brains store familiar musical patterns and structures in long-term memory. This includes melodies, rhythms, harmonies, and even specific songs we've heard before. Pattern recognition. Statistical learning. Our brains are adept at recognizing statistical regularities in the music we hear. For example, certain notes, rhythms, and chord progressions are more common in specific genres or styles of music. Schema-based recognition. We develop mental templates, schemas, for different musical structures, such as the verse-chorus form in popular music. When we hear a piece of music, we match it against these templates to understand and anticipate its structure. Predictive coding. Expectancy theory. Our brains constantly generate predictions about future events based on past experiences. In music, this means predicting the next note, chord, or rhythmic pattern. Error detection. When the music deviates from our predictions, it creates a prediction error, which can be surprising or pleasing, depending on the context. This error detection helps us refine our predictions and enhances our enjoyment of music. Neural mechanisms. Auditory cortex. The primary and secondary auditory cortices are crucial for processing the basic elements of sound, such as pitch, timbre, and rhythm. Prefrontal cortex. This area is involved in higher-order cognitive functions, including the anticipation and prediction of musical sequences. Basal ganglia and cerebellum. These structures are important for processing rhythmic and temporal aspects of music, contributing to our sense of timing and beat. Reward system. Dopaminergic pathways, including the nucleus accumbens and the ventral tegmental area, are involved in the emotional and reward-related aspects of music listening, particularly when predictions are met or exceeded in pleasurable ways. Emotional and cognitive integration. Emotion and expectation. Music often evokes emotions by playing with our expectations. For instance, a resolution of tension in music can provide a sense of relief and pleasure. Attention and focus. Paying attention to music involves both bottom-up, sensory-driven, and top-down, cognitively-driven, processes, allowing us to pick out important features and anticipate future elements in a piece. Conclusion. When we listen to music, our brain distinctively responds to each tone forming the memorized sequence, with the auditory cortex responding first and sending information to the hippocampus and the anterior and medial cingulate gyrus. Thanks for watching. Request you to subscribe the channel.